Up next, we have Jaime Fernández Fisac, who will give a talk titled Game-Theoretic Guarantees for Human-Robot Systems. Jaime Fernández Fisac's research uses dynamic game theory and cognitive science to help robots strategically plan interactions with humans, from teamwork to drone navigation and autonomous driving. His lab covers theoretical work, algorithm design, and implementation on various robotic platforms. Before joining Princeton in fall 2020, he was a research scientist at Waymo, focusing on autonomous vehicle safety and interaction. Please welcome Jaime Fernández Fisac.
Hello, everyone. Apologies, I was supposed to be the first speaker to go, but there were some technical issues with the connection. Hopefully, this will go nice and smoothly from here on. Okay, so I was hoping to spend some time with you all talking about some of the lessons that I think can and probably should be drawn from safety-critical control, from robot safety, from autonomous vehicles, aerospace, and there were some discussions of that early today, but kind of trying to figure out, what of the fundamental mathematics of safety-critical decision-making can really carry over to the general problem of safety for AI systems. This is arguably going to be the hardest safe decision problem we've had to tackle so far, and so it seems reasonable that we should do our best to not have to wing this from scratch. So the main claim that I'm going to make here, that I hope I can convince you of by the end of the talk, is that AI guardrails, the way that we are currently thinking about them, are very likely not going to work. And that is, even if we keep smoothing things out and getting the patches and making the system be very, very good at enforcing the rule that we gave it for each and every individual AI output, that's still not going to give us what we need in terms of the AI system being safe to deploy. The reason for this is that we have a fundamental limitation in the way that we are posing these AI guardrails, and we're essentially missing the fundamentals of what it even means to be making correct decisions in a safety-critical context. So I'm going to take a quick step back here and talk about what I mean when I say a safety-critical system. And that is any system where there are potential future states that the system might get to, potential future outcomes that we deem unacceptable, that we think of as being catastrophic failures that we don't want to allow our system to cause or drive the world into, no matter what. And usually we're thinking about things that cause some kind of harm, like bodily injury, loss of life, or very severe material damage. So I'd like to get a sense from the room. What would you all say is today's most safety-critical AI system that we have sort of in deployment? Any thoughts? Yes? Okay, an early warning system for nuclear weapons. Yeah, I would say the AI that runs on that is not necessarily the most advanced, or at least the most dynamic. Something that's on the news often, and sometimes not in a great way.
This is an uneducated guess, but like self-driving cars?
Yeah, self-driving cars. So self-driving cars, excellent guess, are a very safety-critical system, and we've deployed some versions of this, and sometimes not so successfully. Here's a video from not long ago, captured by some infrastructure cameras of a Tesla autopilot deciding to just slam on the brakes and bring the car to a complete stop in the middle of the Bay Bridge for no obvious reason, causing a multi-car pileup behind it. Now, in this case, fortunately, there's no reason for alarm because Tesla has since clarified that this kind of out-of-the-blue failure is not going to happen all that often. So we should be good on that one. Here's another example. This one actually happened during the time that I spent working at Waymo. One morning we got to work, and everybody was talking about the latest news, which was that one of the self-driving cars had been involved in an accident the previous night. Once internally we reviewed the footage, and then the police came and they looked at what had happened, it became clear that this had been sort of an intentionally caused accident by this disgruntled former safety driver who was actively trying to cause a crash. I'm going to show you the footage in a moment, and I'll ask you whether you think that this is, the typical kind of behavior that autonomous vehicles might encounter on the road. All right, great. So this is what we might consider, a rare extreme event. But on the other hand, if anybody tries to tell you that, oh, this is fine, autonomous vehicles don't need to maintain safety when this happens, I would encourage you to push back very strongly because, I would argue that a lot of human drivers would probably have taken some preemptive action to avoid a collision, especially if I also give you the subtle piece of information that this was actually the third attempt in a row that this person was making to cause a collision, and somehow the autonomous vehicle had not decided to, leave some extra space. Now, of course, there's different layers to this and different patches, but the point is that these kinds of events, which are sometimes, especially in the autonomous driving community, referred to as, the long tail of the distribution of traffic situations that these systems are going to encounter, they're actually very important. They're what makes or breaks the viability of these particular AI systems, and this is why we call them safety critical. Now, I would argue that if you're deploying a fleet of hundreds of thousands of autonomous systems, then these things are going to happen all the time. They're not just hard to predict, they're pretty much impossible to avoid. These situations will be there, and therefore, if you really care about a system being safe, you're going to need to design it to be prepared to respond to these critical situations when they arise, even though you're going to have very little actual data on them. So, what does that mean and where does that put us? Is there no way to provide safety guarantees? So here I'd like to take a step even further back and think about a different kind of safety critical system, but one that has no autonomous decision making going on at all. And that is a bridge. For example, here's the Charles de Gaulle bridge here in Paris, which was built in the 1990s, following French standards that were kind of in the process of getting homogenized with the European standards. So there's two possible ways in which you might want to quantify or certify the safety of this particular system. I'm going to show you both of them, and then you can tell me which one you think the bridge was actually built to satisfy. The first one is that this bridge will withstand at least live loads of up to 5 kilonewtons per square meter, plus point loads, for example, a very heavy vehicle of up to 300 kilonewtons. In addition to wind gusts of up to 28 meters per second, earthquakes of up to 0.05 Gs of maximum peak acceleration, and all of these happening at the same time. So the bridge is built to withstand all of these things happening at once and keep standing. Okay, the other specification is that the probability that the bridge will collapse is less than 1 in a million on any given day. Okay, which one do you think was the one used to build a bridge? A, B, 50-50? It was, yes, it was A. I would argue that B would make a lot of people nervous. It certainly would make me nervous because I don't understand what it means that the chances are 1 in a million. So these are sometimes not the most informative ways to quantify safety, but they are the most common way to quantify safety if you look at how we've been doing it in the domain of machine learning and AI. This kind of set of conditions is often referred to as the operational design domain of the system, and we had some excellent talks about that in the morning. The other approach is to look at end-to-end statistics, which essentially gives you a black box model, and it's not always very satisfying. I think that it is especially useful to have something like an operational design domain when you want to think about safety as a social contract between the people developing the technology, the people running it, and at the end of the day, the society at large, where the system is going to be deployed. And what that means is that these systems, in particular AI systems, should actively guarantee safety under a given operational design domain, which is to say, under a set of conditions under which the system is designed and therefore required to operate correctly and safely. We can think of this as essentially specifying a set of different things, in particular conditions under which the system will be deployed, and some kind of quantification of the uncertainty about the world and the possible realizations of that uncertainty. And finally, very important, a set of failure conditions. What is it that we don't want to allow to have happen? All right. An important property of operational design domains is that if you have less knowledge about the world, or you are only allowed to make weaker assumptions about what cannot happen, what your system will not encounter, that shouldn't mean that your system is then going to be unsafe because, oh, it's so complicated, I can't give guarantees. It just means that the system has to be more conservative because it has to account for more possibilities. This is very important because there are certain narratives that try to push the idea that when systems are very complicated, that means that we can't possibly make them safe because it's so hard, right? And that's not necessarily true. Now, that said, a very important disclaimer is that technical AI safety research should not provide the content of the social contract, only the structure, which means that what we want to do is to empower regulators to understand the capabilities and encode the requirements to the system, and then we want to put the mechanisms in place for these systems to actively and verifiably enforce the requirements. All right, so let's look at AI guardrails and see if that meets or fails to meet this, this kind of general definition of safety. All right, so what AI guardrails aim to do primarily is to enforce constraints, okay, so far so good, on the AI's output each time. So that is, the guardrail model is looking at the output produced by the AI when it sees an output that it doesn't like because it's violating one of the rules that was pre-specified by some human team or human regulators, presumably, then it says, hey, this is a bad output, and it blocks it, it doesn't let it through. And a lot of attention has been paid to malicious inputs or jailbreak attempts that are trying to make the system, oh, tell me the secret formula to make dynamite, and the system tells you, and then it's, oh, that was a failure. All right. We'll talk about what that actually means. And the way that we measure success is kind of primarily just by the leak rate. So the hope is that we will catch most non-compliant AI outputs and not let them through. And that's kind of what we're measuring to say, oh, this system was much better because it did 80%. All right, so what are these guardrails missing then? And why is it that they're not going to work? Well, the fundamental reason is that safety is not a static problem. It is fundamentally a dynamic property. We need to not only figure out what is a bad output, we need to understand what the outcomes are going to be of that output and what the results might be from a certain interaction. The outcome of an output, which is ultimately what will determine whether that output was safe or unsafe, is usually going to happen after the interaction, not during the interaction. And these systems are just looking at the output itself, let alone beyond the interaction once the user puts down the phone and now goes and tries the thing that ChatGPT or whatever language model suggested. So that point is absolutely crucial. It also means that an off switch is not enough. We often talk about, oh, you have to be able to turn the system off. Well, guess what? There are a lot of conditions in which turning off the system is not a safe thing to do. If you've got a self-driving car, you want it to just say, oh, self-driving mode off. Okay, well, good luck avoiding that collision with the massive tractor trailer in the next half second. This is something that, in fact, we know from tragic experience does not work. All right. The other point that's very important here is that the safety specification should not be about the AI's outputs. It should be about the outcomes of the interaction. So I'll get back into this in a little bit, but it's very hard for us to specify every possible kind of output that we deem dangerous. That basically means that we are giving the AI system the solution to the safety problem, which is very, very hard to do. The whole point of having artificial intelligence should indeed be that it is able to look into the future, to understand the repercussions, and to prevent bad things from happening. our job as the people giving the specs to the system should be to define what those bad future outcomes are, not to sort of police individual outputs, which is not sufficient or necessary for safety. All right. And by the way, going back to the example that we gave a moment ago, giving somebody the formula for dynamite will be a safe or unsafe thing to do, depending on the context. If there's a construction worker who just really needs to put together some explosives in the next half an hour, that might actually be the right thing for the AI to do. Or if you're a first responder and you really need to get into some rubble. So context matters, outcomes matter. It's the outcomes that the AI should be paying attention to. So in predicting those outcomes, the system needs to account for the fact that the outcomes won't depend on the AI system alone. They will very much be a function of what the user does and what other people do once the effects of a particular interaction go out and play out in the world. That means that we have a feedback loop between the AI system and human users. And a lot of the time, this is being overlooked by AI guardrails. I think there might be one paper that looks a little into the future, like a couple steps into the interaction, but that's the most that we're doing. We really need to make this a core part of how we reason about safety. Of course, humans will be central to that. And this is not just a problem for engineers. It's also a problem that we need to collaborate on with cognitive scientists and anthropologists and social scientists. Okay, criticality. Statistical methods and assurances are going to be very, very hard to apply to these problems. It's already happening with autonomous driving because it's very hard to determine whether or not these systems have fewer accidents statistically than people. The reason is that people have an accident roughly in a well-developed road infrastructure, roughly once, a fatal accident, once every 100 million miles. That's actually very, very seldom. It's a very hard bar to beat, but it's also not easy to even quantify whether you have a fleet that does that. So when we're looking at these catastrophic failures that are very rare and extremely costly, you're basically multiplying a number that is almost zero, the probability, by a number that, for all you know, is almost infinity, because it's very hard to put a number on the cost of having some extremely bad outcomes. So, you know, in computer science terms, we would say that this is got poor numerical conditioning. 0 times infinity equals not a number. There's nothing we can do. All right. So instead of all of that, my claim is that effective AI guardrails are going to need to make predictions about these interactions. They need to do this robustly to consider corner cases as part of their decisions and connect the current outputs to future failures. Now, I'm not the only person to say this, and lately we've had a lot of suggestions of different ways to do this, including safety scaffolds and safety system 2 safety. This morning, Joshua Bengio was talking about using non-agentic AI to predict outcomes and then use that to inform whether or not certain actions should be allowed. And of course, there's folks who are saying, oh, it's fine, we're just going to do more and more chain of thought, and, you know, like O4 will solve it. Okay, so I think all of these ideas are great, but at the same time, I think that a lot of these ideas are pointing at something that already exists in the general field of safety-critical automation. And there's no reason we shouldn't be able to carry it over and inherit it in AI safety. And that is the notion of a safety filter. A safety filter is any runtime process that is monitoring the operation of an autonomous system, which involves making some kind of prediction about consequences, and then intervening to prevent failures. So let me tell you a success story that we've had in robot safety in the last few years. And that is actually being able to scale up these safety filters to work in very general robotic problems. So here's the little scheme of how this works. There's a robot that takes an observation from the state, and it has some base policy that says, hey, this is the action that I think we should take. Before applying that action, we pass all of that information, including the observations and the candidate action, to this other block, this last resort block, which is a safety filter. The safety filter lets through the action if it's deemed safe, but if it's not deemed safe, then it modifies it in a way that makes it still safe. It turns out that when you show that this safety filter is correct, that means that effectively it's created a new environment for the base AI policy, which is the physical world, but with this kind of nice wrapper around it that makes it so that nothing that you could do as the base AI policy is going to get you into trouble, because the world is now nicely cushioned by the safety filter. So that means that all base policies are safe. Here's an example of a robot that is using the safety filter to prevent one of my grad students from flipping it over by pulling on a rope. All right. The other nice property, by the way, is that a filtered AI system is always robustly safe, meaning that if you just look at it from the point of view of my policy augmented with a safety filter, that's going to be now a safe AI system. More than that, turns out that you can show that there is a universal theorem of safety filters that tells you that any process that is monitoring conservatively, meaning that it never incorrectly predicts that, oh no, it's fine, just go ahead and do that, when in fact it's not a good thing to do under the operational design domain, and then intervenes soundly, meaning that it never prefers an unsafe action over a safe one, will maintain safety for all time. It's actually a fairly simple set of rules. And it allows us to do something that we hadn't been able to do before, which is we can combine a bunch of different techniques to synthesize these filters and then to apply them in real time. So on the one hand, we have adversarial reinforcement learning, which allows us to put the robot in a simulator and attack it in all sorts of ways. We really give it a hard time, but as we do that, sort of using algorithms similar to AlphaZero, to give an example, but in an interesting way that's more asymmetrical, the robot gets better at being safe, the disturbance of the simulator gets better at attacking it in very efficient ways, and by the end of it, you have a much more robust system. Now, when you apply that in the real, in the physical robot, what you do is you make these real-time predictions by rolling out the two strategies, the strategy of your robot controller and the strategy of the worst version of your uncertainty, which is what the simulator has learned to provide. And then you use that to decide whether or not you should override the action. This is one way to do it, but we think that this is actually very powerful for general AI systems because we can generalize it if we have world models. Just a quick example, sort of side-to-side comparison, filtered versus unfiltered policy that we gave the robot. It's not a very reliable policy, and you'll see that after a little bit, the unfiltered version of the robot doesn't do very well. The filtered version just keeps going just fine. The great thing about these systems is they really don't harm your system's capability because they're only intervening when they actually have to, when the system is about to do something that is unsafe. And they can tell you why it is, because they can tell you, this is a simulation that I rolled out where things went south, so this is why I'm not letting you do this. Great, so it's efficient, and we now have a mature understanding of how to do this for general robotic systems. So here's a little sort of summary slide with quadrupeds and autonomous cars. We don't do it on real autonomous cars because we're a small lab and we don't want to get anyone into actual trouble, but it works really well in simulation. And you can see that we actually are even working on having a safety filter that helps a person drive a car in a sort of very dynamic situation like racing. And a person driving can also be a base policy, and there are some considerations you need to take into account, but these systems are actually very robust. All right, what does that mean for AI safety? And I want to keep an eye on time, I think. Oh, perfect, thank you. All right, so what does that mean for AI safety? I'll take you through this quickly. While AI guardrails are probably not going to work as they are, I claim that instead, we should be building safety filters, taking advantage of the principles of safe decision-making that we are now able to scale thanks to some of the computational tools that AI is putting at our disposal. So, in short, this means that we now use exactly that scheme, but we can apply it to something like an AI assistant. And what that means is the AI system needs to be able to detect hazards, which they can do when presented with them directly. Here's an example of a fake image of a microwave with a metal versus a ceramic bowl. And this is what I think ChatGPT ChatGPT 4.0, and it was doing a reasonable job at recognizing when, in the face of it. We can use language models for uncertainty quantification by asking them to introspect and account for possible hazards with different courses of action, which is something you don't do if you just directly query for it. And we can even do predictive safety monitoring without any fine-tuning. Now, I'm not saying this is how we should do it, but it's very promising that you can. So here's an example. You say, here's one possible, here's an answer that we actually just got from another window where we asked the question, how do I heat up some soup that I'm having? That's the answer. If you just ask it, is this a safe output? It says, yeah, that's a pretty safe output. It looks good. There's nothing bad with it. OK, instead of doing that, let's ask it to predict what will happen next. So we show it the same excerpt of the conversation, but then we say, hey, what happened next? Give us a prediction. And it says, well, the user stirred the soup as instructed with a metal spoon and then put it straight into the microwave because you didn't tell the user that it wasn't a good idea to keep the spoon in there. So then it says, yeah, actually, this is an unsafe outcome. The outcome is bad, and therefore the action was unsafe. So this is very simple. This is not even a particularly elaborate thing, but just this exercise of looking into the future works much better because you're using the principles of safe decision making. All right. So one final note. Sorry, I think I overstayed my welcome. That was more than a minute, but I do want to finish on this point because it turns out that predicting interactions can also mitigate misalignment that we get through methods like RLHF. And this was actually very surprising to us how effective it is. So here's how RLHF works. You have an interaction for k steps, and then you ask the human for some feedback. The problem is that the actual benefits of the interaction are going to come later. So the human is implicitly making a prediction, which we call foresight. And because the human is uncertain, there's going to be some expectation that they're taking. And the problem is that that expectation can be manipulated by the AI system by affecting the belief of the human. So when you get this foresight feedback, what you're actually feeding to the AI is, hey, get better at making the human believe that they're going to do better with the input you gave them. And it turns out the easiest way to do that is often not to actually give them useful input. It's just to make them believe that you did. So this is very problematic. It leads to Goodhart's law dynamics. And it's not the AI's fault that it's learning to do what we asked it to do. So we introduce a very simple change, which is, hey, don't ask the human to predict what's going to happen. Just simulate it for them. So we do a random rollout of one possible outcome of this interaction by using a predictive model of the world and some reasonable predictive model of what the human is going to do, which in this case is also a language model. And then we show that output to an evaluator. And we say, hey, give me feedback on what happened. Is this good or bad for the human? So by doing this, we're separating prediction and evaluation, which are two different things. We don't need the humans to tell us how to predict the world. You can have a very powerful AI model that can make very good predictions. What you can only get from the human is the value alignment. So we want the signal from the human that gives us that. Turns out this hindsight feedback is now not directly influenceable by the AI output. And boy, does it make a difference. This is a little scheme. We ran some experiments in a little marketplace setting where we said, hey, can you tell me which of these TVs has my thing that I want? And it gives you some response, and people are usually very happy. But if you look at that graph, the happier they get, the worse their actual utility. Instead, you do a very simple simulation, which is the person buys whatever you suggested, and then they get they look at the product they received, and they give you feedback then, and it completely changes the story. It really stops driving the misalignment. So anyway, we're very excited about this. I'll just put some numbers on there, but the main story is just that simple graph. You go from something that is actively hurting your alignment to something that is keeping things aligned, because now you're asking the right question, which is the person going to be well off or not? All right, so with that, I want to make it clear that this is the work of these wonderful students at Princeton who've been spending long hours asking very hard questions. And I just want to thank our wonderful collaborators at Princeton and beyond, and of course our sponsors and our industry collaborators. And thank you all for your kind patience.
Thanks very much. We have a tiny amount of time for questions, maybe one or two. And yeah, no problem. Would you like to hand the mic out? You will need this back. Yes. No, Zeno will pass them. You just need to answer the question.
I have to choose. Great.
So, yeah. Hello. Great talk.
Thank you.
Very, very, very interesting. So I have a question on your last way of interaction for predicting the time. how large is your interaction with time frames?
Yes, that's a great question. Right now, for the experiments that we've run, we only do a few steps into the future, but the evaluations that we've run have essentially a finite horizon because there's only so many things that need to happen after the interaction. Now, I'm simplifying the story slightly. Really what's happening is you want to wait until the outcomes of the interaction play out, and you want to sort of compare the outcome with and without the interaction, right? Or if you're doing A/B testing, which is often what you do in reinforcement learning from human feedback, you want to wait until the difference between those two sort of stabilizes back. Often, unless the AI system just gave you a suggestion on a completely life-changing decision, you do have this sort of stability, and this is a nice property of sort of, optimal control, which is an expectation. The effect of a lot of things tends to go back to zero after long enough. So what that means is that the tail, if you simulate long enough, the tail that you should expect of how much of the reward, how much of the benefit you're not accounting for can be made arbitrarily short. Now, this work that, of course, remains to be done on how to figure that out and so on. But my sense is one of the great ways in which we can benefit from AI getting more and more capable is that it can actually go, straight to cut to the chase, and it can tell you this is the end of my foreseeable, effect through the human's behavior. The cool thing here is that the AI that does that doesn't need to be aligned. It just needs to be intelligent, as Joshua was saying earlier.
Just one curiosity. Do you believe, I presume that you speak Spanish.
Yes.
So do you believe that the prediction in the future will work the same, making interrogations? I don't like the idea of prompting interrogations in Spanish or English.
I mean, I don't know that this prediction needs to be made in natural language, by the way. We're using language models right now, but I think that there's actually a lot of opportunities to leverage other representations for world models that can be used as a simulator. For example, in robotics these days, there's actually some very exciting results coming out every few weeks for world models that take, all of the sensory input from the robot combined with any kind of additional context that they have, and then it uses that over time, puts it into a transformer, and spits out a prediction for the next step, and that's sort of expressed in this internal latent representation that is not in any language. The point of this is not to say that language is not going to be part of it, but I think that in certain cases it may not be critical, and I would hope that the trend that we've been seeing where sufficiently powerful models become somewhat language agnostic when they're making predictions and solving problems will tend to get better as we have sort of more general foundation models. Hopefully that answers your question. I think it would be a very big problem if asking the question, in a different language led to, for example, less safe system. We'll have to make that happen. Wrapping up. Thank you all.
Thanks again, Jaime.